Okay, well, yeah, thank you for the invitation to speak here. I'm sorry I can't be there in person right now. Uh, I'm a new faculty member at the Hebrew University of Jerusalem, and I'm new to Israel, so there were a lot of you I was hoping to meet in person, but hopefully sometime soon once Corona has receded. So over the next 15 minutes, Yair and I will be discussing the ultraviolet properties of tidal disruption events, or TDEs. TDEs are a somewhat newer and somewhat more specialized type of transient than a lot of the things we've heard about already. So I'm going to try and offer a brief introduction to the basic physics of what they are, and also highlight to some extent both the things that we do know about them and the things that we're pretty sure we don't fully understand yet. So the basic picture of a TDE is pretty well illustrated in this cartoon by Martin Rees. In the center of a typical galaxy, you have a supermassive black hole. And every now and then, an unlucky star will wander too close to the supermassive black hole. From the star's perspective, too close means the Roche radius, which in units of Schwarzschild radii is between a few to maybe a few tens of Schwarzschild radii. If the star does come within that Roche or tidal radius, it gets torn apart by the tidal field of the black hole. Roughly 50% of the star is dynamically unbound and escapes to infinity, but the other half of the star remains bound to the black hole on very eccentric trajectories. So it expands out into thin, dynamically cold debris streams with eccentricities that are at least 0.99. These debris streams come back to pericenter after a period of 1 to a few months, and then through processes we don't fully understand yet, dissipate their orbital energy and assemble themselves into some kind of accretion flow. And it's the combination of energy dissipation during the circularization process and the release of power by accretion itself that powers the multi-wavelength transients that we see from galactic nuclei and think are tidal disruption events. Our current sample of TDs is relatively modest. I'll talk more about it at the very end of this talk. But we've seen, I would say, a few dozen nuclear flares that we can be fairly confident are tidal disruptions in origin. These are uncommon, but they're very dramatic. They're multi-wavelength flares, so they go all the way from the radio, and in cases where a relativistic jet is launched, up into the hard X-ray. They're very bright, brighter than a typical supernova, and usually in a bolometric sense, only modestly dimmer than a superluminous supernova. They are interesting for a number of different reasons. We won't have time to go into depth on all of these, but I'll just mention them quickly here. So I think the original and in many ways the strongest motivation for studying TDEs was and is to use them as probes of supermassive black hole demography. So as I think everyone here knows, the average supermassive black hole in the universe lives in a quiescent galactic nucleus that is very far away from us, meaning that we can't do dynamical modeling of the unresolved starlight to get at its mass, and we don't have a steady state accretion disk, or AGN, to give us an alternative probe of its mass or its spin, as can sometimes be probed with accretion disks. But every supermassive black hole will eventually tidally disrupt a star that comes close enough to it, and the accretion luminosity from that tidal disruption event lights up the quiescent galactic nucleus and gives us a way to measure or constrain the properties of the black hole responsible for the disruption. We also know, from a theoretical perspective, that the initial rates of mass fallback onto the supermassive black hole are typically super Eddington. So it varies depending on the mass of the black hole and the mass of the disrupted star, but in a typical TDE, you expect a peak mass fallback rate that's between 10 and 100 times the Eddington limit. This is a pretty poorly understood regime of accretion physics. So if that mass fallback rate is converted into an accretion rate, this gives us a relatively unique laboratory to study the physics of super Eddington accretion flows. The overall rate, either in a volumetric sense or a per galaxy sense, at which supermassive black holes tidally disrupt stars, gives us information about the nuclear stellar dynamics of galaxies, the ways in which dense star clusters living in the central few parsecs of a galaxy scatter off of each other and evolve their orbits over time in a way that can't really be studied outside of the local group normally. Getting into some more speculative motivations for studying TDs, we know that at least a minority of tidal disruption events launch powerful relativistic jets. So far, we've only seen 3 examples of this, the most famous one being Swift J1644. These relativistic jets are very interesting in their own right. They're kind of like ultra long GRBs, lasting for durations of order 10 to the 6, maybe up to 10 to the 7 seconds. But one particular thing that's interesting about them, which was examined by Glenys Farrer and Tzvi Piran, is that these are plausible acceleration sites for a large fraction of the ultra high energy cosmic rays in the universe. And then getting to maybe the most speculative motivation I'll talk about here, there are a number of theoretical works, including one of mine back in 2011, suggesting that a burst of tidal disruption events can be expected to follow the low frequency gravitational waves emitted when 2 supermassive black holes coalesce with each other. So unfortunately, this is the kind of multi-messenger astrophysics that may not overlap with the time duration of the Ultrasat mission, because this would be an electromagnetic counterpart to a LISA band gravitational wave signal. But in principle, these can be used as standard sirens if they accompany the gravitational waves from a supermassive black hole binary merger. Now, from a theoretical perspective, if you want to compute how often TDEs happen, you compute the rate at which stars diffuse off of each other through 2-body scatterings in phase space into a structure called the loss cone. And since I'm speaking remotely at the Weizmann Institute, I should mention that the late Tal Alexander was one of the real experts in this and has a really excellent review article on this subject from 2017. Observationally, observers infer TDE rates between 1 disruption every 10 to the 4 years to 1 disruption every 10 to the 5 years in typical galactic nuclei. These rates are in modest tension with theoretically predicted rates, which are marginally consistent to maybe 1 or 2 orders of magnitude higher. And as an example of a theoretical rate prediction, I have this plot right here. On the y-axis, we have the volumetric event rate, TDEs per cubic megaparsec per year. On the x-axis, we have the black hole mass. And the 5 different curves correspond to 5 different assumptions about the bottom end of the supermassive black hole mass distribution. This is a really important astrophysical question, which we know very little about right now. It has great bearing on how supermassive black holes formed in the early universe and what the masses of their seeds were. And depending on what you believe about supermassive black hole formation, you might expect that in the low redshift universe, there are no black holes below 10 to the 6 solar masses, or you might have a more generous estimation. Maybe there are intermediate mass black holes in dwarf galactic nuclei. It turns out this is one of the key unknowns setting the volumetric TDE rate. And you can see the per galaxy rate color-coded on each of these curves. I think at this point, this tension or discrepancy is probably due to the fact that there is, empirically speaking, a very steep luminosity function for tidal disruption events, and we haven't yet measured the bottom end of it. So over the luminosities that we've sampled through current time domain optical and UV surveys, we see a luminosity function that goes roughly as L to the minus 2.5, but we don't see the bottom end, we don't see any kind of turnover. And I think this is something that Ultrasat might be able to make major progress on, allowing us to really estimate an accurate volumetric or per galaxy event rate, which in turn would tell us something immediately about the occupation fraction of black holes in dwarf galactic nuclei. And if we had some way to take the light curves or SEDs of TDs and turn them into black hole masses, this would give us the actual bottom end of the black hole mass function, which would be a major coup. So how can we do that? Well, for a long time, theorists have constructed what I would call naive TDE models. And the basic idea is this. If you assume that the mass fallback rate, which at late times goes as this famous T to the minus 5/3 power law, and has a characteristic decay time of about a month, is efficiently translated into an accretion rate through a compact accretion disk, because the matter returning to pericenter efficiently circularizes into a disk. And I should mention right now, this is a fairly big assumption. Then we get a brief phase of super Eddington accretion, which may be accompanied by powerful outflows or jets. And after that, you get a fairly typical multicolor black body soft state disk. And the peak of the spectral energy distribution is in the unobservable extreme ultraviolet, but you have a Wien tail extending into the soft X-rays, and optical and near ultraviolet emission shows up on the Rayleigh-Jeans tail. If you take these kind of naive TDE models, you get emission in the ultrasat band of order 10 to the 42 ergs per second. I say this is a naive model because, as Yair will explain in a minute, observed TDEs are far brighter than this in the near ultraviolet at early times. But I put naive in quotes because even though this doesn't really do a good job of describing early time TDE emission, probably because of the messy details of the circularization process, recent work has shown that this simple, essentially Shakura-Sunyaev-like disk does a fairly good job describing late time emission a few years after the peak of the light curve. So with that basic summary of the theory of TDEs, I think now's a good time for Yair to take over. Yair, would you like to take the helm?
Sure. Yossi, can you tell me if you can hear me okay?
Yes, we can.
Okay, great. So as you just heard from Nick, the theorist told us to look for things for accretion disk emission at X-ray and extreme UV, and we observers rebelled and found things at 10 times lower temperature and larger blackbody radii. So there are TDEs in the X-ray which fit the expectations, but there is this class that I'm going to focus on because it's more relevant to ultrasat of events that are 30,000 Kelvin, and so they peak the emission in the UV. And so this is the first of these events. You can see the light curve on the left and some spectra on the right. And the thing I want you to notice is that the bottom spectrum, the bottom panel, is day 254. It's still very blue. There's still a very underlying blue continuum. So this 30,000 Kelvin UV peak lasts for hundreds of days, which is also how we distinguish these things from supernovae that cool much faster. And so there is this class of events that peak in the UV, not as expected, and they stay that way, very blue, for very long. So Nick, if you could advance to the next slide, sure, please. So now, as Nick mentioned, we know of a few dozen, about until recently 10 to 15. ZTF recently tripled this sample, so it's a few dozen events. The light curves are kind of similar. As Nick mentioned, we don't know exactly the bottom of the luminosity function, but there seem to be some fainter events. But most of the ones we're finding are quite luminous. And we have this way of identifying them based on their optical spectra. And so the question is, why are these TDEs if they're in the wrong wavelength? And there are currently two explanations for this that Nick will go into in more detail. I'll just mention that we are seeing the accretion, but it's being reprocessed by some material that's then emitting it at a larger blackbody radius and lower temperature. Or that we're seeing the processes that happen before the accretion disk is formed, where the debris is still circularizing and creates shocks in the outer part of the stream, far from the supermassive black hole. And these shocks, these outer shocks, emit at these temperatures. And so maybe we're seeing the processes before the accretion. And so these are the kind of the two models. Again, Nick will go into them in more detail, but I want to show you some more observations. So next slide, please, Nick. Mm-hmm. Okay, so there are, okay, thanks. So there are a couple of events now that show these double peaks in the UV. So you're seeing a light curve from the optical to the UV. On the left is SASN 15LH. I'll just say for the record, some people don't think it's a TDE, but they're wrong. And on the right is a newer event that they show this kind of fading of the light curve, and then either a plateau or a second peak, and it's most pronounced in the UV. And one of the interpretations is that here we're seeing both explanations for the UV. First is the outer shocks, and then it's the reprocessed accretion. And depending on the properties of the black hole, these two peaks are separated or not in different events. So this is one line of evidence where we might be understanding the emission mechanism, and UV is critical here. Next slide, please. And another thing is at very late times that there is evidence for excess UV emission hundreds of days or even more after the event. So what you're seeing here are several events, and you're seeing this T to the minus 5/3 expected decline, and then you're seeing a late time point that in some cases is much higher than that expected decline. And the interpretation there is that this is evidence for an accretion disk lasting out to late time. So again, this is something that Ultrasat will be able to probe for previous TDEs, but also for new ones, depending on the length of the mission, if there is this excess UV at late times, and if that is evidence for an accretion disk or not. I just want to add that this is very, the wavelength of Ultrasat is ideal for this, but the time scale is not exactly, we don't need this 15-minute cadence, we think. Nick can later elaborate if there are expectations for emission variation on those timescales. I'll just say that there is one TD observed in the optical by test, and there's no short timescale variations there. It's very smooth. But this brings up one thing, maybe for the discussion I wanted to bring up for the data analysis part, is that stacking images will, since we don't need the time resolution, will give us much more depth to probe these late time accretion disks, but also to find younger TDs when they're young. Okay, so I think I have just one more slide that's not UV related, but is a mystery that it will help with finding more events, which Ultrasat will be good for, might help solve this. Nick mentioned this briefly, that when you look at TDE host galaxies, most of them are concentrated in this corner of phase space, which I won't go into the details, but the gray area is where galaxies generally are, and the the red points are where TDEs are, and you don't need to understand what the axes are to see that there's something weird going on here. Why are all TDEs concentrated in that part of phase space, which belongs to post-starburst galaxies? And there are several ideas, but the more events we find, the more we can quantify this preference and maybe understand it better. So just another reason to want to find more events. Okay, I think Nick, it's back to you.
Okay. In the interest of time, I will go a little quickly through the next couple of slides. Essentially, as Yair said, the TDEs that we observe with spectral peaks in the near or far ultraviolet look very different from the simple theoretical predictions of a bare accretion disk. And we think that a lot of the reason for this is due to the complicated details of the circularization and disk assembly process. For various technical reasons, this is a very difficult problem to simulate on the computer from first principles. And at this point, I would say there are really no fully self-consistent simulations that have been done in the literature. And our understanding has come through a number of different approximations. The initial phase of the TDE accretion flow probably retains significant eccentricity, and in addition is probably inclined with respect to the black hole equatorial plane. But at late times, there is reason to believe that these disks should settle down into something more like a standard accretion flow. So at early times, as Yair said, there are, I would say, currently two competing ideas in the literature about how to explain the large optical and UV photospheres that we see. One idea is that we do have some sort of central engine, an efficiently circularized accretion disk, but this central engine is enshrouded by a large-scale reprocessing layer. So the accretion disk extends out to maybe 10 Schwarzschild radii, but the reprocessing layer sits out at about 1,000 Schwarzschild radii. And this can be a bound quasi-hydrostatic layer of poorly circularized debris, or it can be an outflowing wind that is launched from the disk. There are a couple of varieties of this model. In the second picture, which my colleague Zvi Piron has done a lot to develop, there is not necessarily an accretion disk at all close to the event horizon of the black hole, but instead the early time luminosity that we're seeing is due essentially to shock power at larger radii. As streams pass around pericenter, they come back to their apocenter and shock heat against each other, thermalizing their kinetic energy, which can then be radiated from large radii. Right now, we don't know which of these pictures is right. In my opinion, probably one is correct in parts of parameter space and the other is correct in other parts. But expanding our sample, as Ultrasat is poised to do, would potentially do a lot to help solve this problem and allow us to build first principles models for TDE emission. And when I say Ultrasat is poised to expand our sample, here is kind of a quick and dirty estimate I made this morning for the potential discovery rate from Ultrasat. So take this with a grain of salt. But here I've tried to list the existing number of discovered TDEs, as well as predictions in the literature for near future surveys. So currently, we've only seen a few dozen TDEs. The present day detection rate is dominated by wide field optical surveys like Assassin and especially. Oh, can you hear me?
Yes, now yes.
Okay, sorry about that. Let me know if there's trouble again. So the present day detection rate is dominated by wide field surveys like Assassin and especially ZTF. ZTF released a very nice catalog of 20 new TDEs at the beginning of this year. In the immediate future, I think our biggest improvement in TDE hunting is going to come from eROSITA and its all-sky X-ray survey. But because soft X-ray emission is on the vene tail of the spectrum from the inner disk, the number of TDEs detected by eROSITA depends crucially on the unknown spin distribution of black holes in the universe. So eROSITA could find a few per year under very pessimistic assumptions, or thousands per year under optimistic assumptions about black hole spins. Shortly after that, LSST will detect of order thousands per year, but the poor planned cadence of LSST in combination with the low cadence for multiband coverage means that their identification efficiency of TDEs could be as low as a few percent. So they might find transient emission from thousands per year, but they might only be able to identify that emission for dozens per year unless they have a multi-wavelength counterpart survey like Ultrasat that they can correlate their detections with. So I think this is a really valuable opportunity for synergy. But if I run the numbers on Ultrasat itself, and if I try to be conservative, so I say we need a limiting magnitude of 21.5 for robust identification, and there's a peak UV luminosity of 10 to the 43.5 ergs per second, which is on the low end for observed TDEs, then an all-sky survey done with Ultrasat that is not cadence limited, and for TDEs not cadence limited means a cadence of once every week or two in a single patch of the sky, would easily find thousands per year and would blow everything else out of the water. The current survey strategy is not totally clear to me. This might be because I'm a naive theorist and need to read more closely. If you really are just staring for a long period of time at 200 square degrees, then you can divide these numbers by a factor of 200 or so, and you will still have an impressive sample, but it would not be achieving what you could do with an all-sky survey. So I think this is a good place to wrap up. I've gone a little over time, sorry about that. Just to summarize, I think the TDEs we see are peaked in the near or far ultraviolet. So Ultrasat has the potential to revolutionize our understanding of TDE science, both understanding the underlying physics of TDEs and also using TDEs as probes of supermassive black hole demographics. And to really maximize this, the more of an all-sky survey Ultrasat can do, in my opinion, would be the better.
Okay, thanks. Due to the lack of time, I'll allow for one or two questions. Do we have either from home or here?
Can I make a remark?
Yes.
Hi. One thing which I want to add is, do you hear me?
Yes.
One thing that I want to add, if the aftershocks model is correct, which will be identified from these observations, then we can have using it, we can have an independent estimate of the black hole mass, which does not depend on the bulge mass relationship, which is usually used, and it's especially doubtful at low end of masses of black holes. So this will be a nice addition to the scientific benefits